So now we will prove a logical equivalence using a truth table. So our goal is to show that the biconditional P if and only if Q is equivalent to the expression P and Q or not P and not Q. So how are we going to do this? We're going to do it with a truth table. So we're going to write a truth table for everything. And essentially the P if and only if Q appears in this column here, and the part on the right hand side appears on this column. And if we're able to show that these two columns are the same, we will be able to see that that means that this expression is true if and only if this one is true, and same, this will be false if and only if this is false. So let's do this. So we start with our variables, P and Q, and we list out all the possibilities. So they can be both true, P can be true, and Q can be false. Then you can have P is false and Q is true, and you can have both of them false. Okay, so now the left-hand side, you can, we saw already the biconditional truth table. It's true when both of them have the same value. So it's going to be true when P and Q are both true and when they are both false. And it's going to be false in the other cases. So this will be true, false, false, true, right? And that already gives us the left-hand side. So with that, we have the left-hand side. Now let us build the right-hand side. Okay. So to build up the right-hand side, one way we can do this is to slowly progress towards it. So since we're going to need, P, Q, P and Q, we're going to need also not P and not Q and the and then finally we do an or. We can do this by steps. So let's start with the negation. So if you have P and P is true, then not P is false. So you get the following. So in other words, this column here is just the same as this column, but with true swapped with false and false swapped with true, right? Same for not Q. So if Q is true, then not Q is false. If Q is false, not Q is true. If Q is true, not Q is false. And if Q is false, not Q is true. Okay. Now let's look at the and, P and Q. So we know that P and Q is going to be true only when both of them are true. So P is true, Q is true, then this is true. But if any of them are false, the and will be false. So this is what this looks like. Okay. Now let's look at not P and not Q. So again, the same thing. This will only be true when they are both true, which is in the fourth column. So this will be true here, because that's the column where not P and not Q are true. So this will be true. So that's the row actually. And then for the other rows, at least one of them is always false. And so this will always be false. And finally, our right-hand side that we were interested in, so this part over here, that's just going to be an, an or of, let me indicate, of these two parts. So it's just an or of these two. And we already saw that the or is true when at least one of them is true. So for the first row, if P and Q are true, for the first row here, you have true, false, which then, so true or false, which gives you true. Oh, I messed up the color here. So for the first row, you have true or false, which gives you true. Then you have false or false, which is false. You have false or false, which is false. And then you have false or true, which is true. And with that, we filled out the whole table. And in particular, we have the left-hand side and the right-hand side. And you can notice that these two columns are exactly the same, which means that for all the possibilities, the left-hand side will always have the same truth value as the right-hand side. And that is exactly what it means for them to be logically equivalent.